On the last episode, we explored the game of cops and robbers on graphs. Sometimes the cop would corner the robber and capture him, but sometimes the robber would evade capture forever. In that case, what happens if you add more cops? How many cops does it take to guarantee they'll capture the robber? The game of cops and robbers takes place on a graph, a collection of vertices connected by edges. The cop picks her starting spot, and then the robber picks his. Beginning with the cop, the two players alternate moving along an edge from vertex to vertex. If the cop lands on the same vertex as the robber, then he's captured and the cop wins. Any graph where the cop has a strategy to guarantee her win, like this, is called cop win. But if the robber has a strategy to avoid capture forever, the graph is called robber win, like this. Last episode, we found a way to characterize all graphs as cop win or robber win. This time, we'll focus in on the robber win graphs. If one cop is not enough to guarantee the robber will be caught, then the police department of Graphtopia would likely send more cops. If there are several cops on the graph, they all move at once, alternatingly with the robber. You can put a cop on each vertex, but Graphtopia can't afford that. So let's try to optimize how many cops we need. What's the minimum number of cops required to guarantee that the robber will be caught? The answer to this question is the cop number of a graph. We'll abbreviate the cop number of a graph G like this. What's the cop number of a cycle? Well, one cop isn't enough. It'll take two cops to guarantee capture. They can move in opposite directions and trap the robber between them. So it has cop number 2. What about the tree? We know from the theorem last episode about pitfalls that it is a cop win graph, so its cop number is 1. But what about the dodecahedron graph? It has no pitfalls, which means that a single cop does not have a winning strategy. Its cop number has to be at least 2. But it has 20 vertices, so if we started with 20 cops and set one on each vertex, they'd be guaranteed to catch the robber immediately. So its cop number can't be larger than 20. There are more clever ways to prove bounds on the cop number. For example, by placing a cop on each of these 10 vertices, there's a cop on or adjacent to every vertex. So they'll still catch the robber on the first round. The cop number can't be larger than 10. Actually, a pretty amazing theorem tells us that the cop number of the dodecahedron is much smaller. The cop number of any planar graph, meaning a graph that can be drawn in a way that none of the edges cross, is less than or equal to 3. This theorem, whose proof is contained in the references, lets us push the upper bound on the dodecahedron's cop number to 3. So, is it 2 or 3? One more classic theorem can help us. It applies to any graph without cycles smaller than 5. In other words, the quickest non-overlapping path from a vertex back to itself, which is called the girth of a graph, must take you through at least 5 edges. So, this graph has girth 5, but this one has girth 3. For any graph with girth at least 5, the cop number is greater than or equal to the minimal degree of the graph, the smallest number of edges coming out of a vertex. This theorem makes some intuitive sense. If every vertex has at least d adjacent edges and there are d-1 cops, then the robber can always escape through an unguarded edge. The assumption that the graph doesn't have any cycles smaller than 5 eliminates the possibility that a single cop could guard multiple edges. The fact that there are no cycles of length 3 means that a cop who is directly threatening the robber cannot also guard another neighbor of the robber. And the fact that there are no cycles of length 4 means that any cop who is waiting 2 steps away from the robber, guarding one of the robber's neighbors, cannot also be guarding another one of the robber's neighbors. It really takes D cops to ensure that the robber can't always escape through one of the D or more edges that emerge from each vertex. The dodecahedron has girth 5, and every vertex on the dodecahedron has 3 adjacent edges. So, by the theorem, it has cop number at least 3. Combining this with our previous results, the cop number is exactly 3. Here's a fun game. Can you construct a graph with an arbitrarily large cop number? In other words, if I give you a big number, like 10,000, can you give me back a graph whose cop number is at least 10,000? Try it yourself. It's not easy, but it's definitely possible. My favorite example is the skeleton of a hypercube. It's a point in 0D, a line in 1D, a square in 2D, the outline of a cube in 3D, and so on. To go up a dimension, you make 2 copies of the previous cube, separated by 1 unit in the new dimension. Then you connect the analogous points in the 2 copies by edges. As you continue to do this, making hypercubes of higher and higher dimension, the cop number goes up. In fact, for the hypercube of dimension n, it's n plus 1 divided by 2, rounded up. This gives us graphs with arbitrarily large cop number. Despite all these impressive results, theorems that give upper and lower bounds on the cop number, and constructions of graphs with huge cop number, there's still a lot that's unknown. An elegant and still unproven problem is Mandell's conjecture, which states that the cop number of a graph grows like the square root of n, where n is the number of vertices of the graph. In other words, there exists some constant k such that the cop number of a graph with n vertices is less than or equal to k times the square root of n. But just because a graph is big doesn't mean its cop number is big. In fact, the graph can be infinitely large and have cop number 1, like this. It's a tree with branches of length 1, 2, 3, 4, and so on. Each branch is finite, but the whole tree is infinite. The cop has a pretty straightforward winning strategy. Start at the base of the tree. The robber is forced to start on one of the finite branches, and the length of that branch determines the maximum time until the robber gets caught. The robber can pick how long he's on the lam for. There's a ton of fun variants of cops and robbers. You can play it on an infinite graph, as we just saw, or you can play a game with imperfect information. In the standard game of cops and robbers, both players know where the other one is at all times. It might be more realistic to assume that each player can only see vertices a short distance away. Or the cop can also see a few distant vertices using some kind of surveillance technology. Of course, changing the rules is likely to change the cop number of a graph. Check out the description for a great reference book about cops and robbers and its many variants. There are also stochastic or random versions. The drunken robber moves randomly. He's equally likely to move to each of the adjacent vertices. The cops want to devise a strategy not just to catch the robber, but to do so in the shortest average time. One fantastically named variant is called lazy cops and robbers. In lazy cops and robbers, there can be several cops on the graph, but only one cop is allowed to move per turn. The lazy cop number is the minimum number of lazy cops it takes to catch the robber. In some cases, they are just as efficient, but in other cases, it takes more lazy cops. I'll leave you with this week's challenge problem, which was inspired by a forthcoming article written as part of a fantastic undergraduate research project. Details in the description. Can you compute the cop number and the lazy cop number for these 2 graphs? Email us your answer at pbsinfiniteseries@gmail.com. See you next time on Infinite Series. You all thought of a lot of fun ways to change the parameters of the game of cops and robbers. Some of you anticipated variants we discussed in this episode, like Yalapu, who mentioned random movement and partial knowledge or limited vision. Joshua Zielinski asked how much things would change if the robber must move on their turn. Are there graphs that have essentially a Zugzwang type situation? Confession, I'm not a chess player and I had to look that up. Merriam-Webster defines Zugzwang as the necessity of moving in chess when it is to one's disadvantage. Fair enough? Yes, if we forced the robber to move every turn, which is known as the active version of cops and robbers, then the robber might lose on graphs it would win in the passive version, the one we've been discussing. This graph is a cop win in the active version, but a robber win in the passive version. Lots of folks ask about infinite graphs. But as Brendan Sullivan, one of the mathematicians whose research is linked to in the description, pointed out, you need to change the notion of how the cop wins. One natural definition is to say the cop wins if the robber is not necessarily caught, but at least forced to move infinitely far away from his starting location, or perhaps forced to visit a particular vertex infinitely often. See you next week.